Hello and welcome everybody. We're really excited for you to join us here. We love the data community. We're happy to be sharing more with you. And, again, we're going to continue to post more blogs, do more talks. We're going to speak at a bunch of conferences. So keep an eye out for us. And of course, if you're doing any events, invite us. We're happy to hear what your data platform teams are doing as well. So my name is Chris. I'm the engineering manager in the data platform team. I'm going to be a speaker and a moderator today. And today I have the pleasure of introducing you to two rockstar engineers here at Grammarly, Christian and Faraz. And during today's session, we'll talk about Grammarly's journey to the Lakehouse architecture, followed by our effort to scale this data platform with a relatively small team. So Christian's going to start us off, give you a little bit of history lesson and tell you how we came to the Lakehouse architecture. So one quick note before we get started, if you have questions during the presentation, you can just go ahead and type them into the Q&A feature at the bottom. We'll address some in the chat and others will promote to the channel and then talk about at the end of this talk. So you don't need to hold them, just go ahead and type them in there and we'll get going. So without further ado, I'll hand it over to Christian to talk to you about our journey to the Lakehouse architecture.
Awesome, thank you so much, Chris. Today, I'm here to talk about Grammarly's journey adopting the Lakehouse architecture and how a team of 5 engineers migrated 7 years of data to the Lakehouse on Databricks. In this current environment at Grammarly, we're trying to do more with our data. We're trying to accelerate product development, unlock new use cases, learn from user behavior, and really foster a culture of data-driven decision-making. My name is Christian Acuna, and I'm a technical lead manager on the data platform team. And today's talk is going to be divided into 3 sections. The first section is going to be talking about our custom-built lakehouse called NAR. And the real meat of my talk is going to be around our data platform redesign, where we built a system called the Event Store on top of Databricks. And lastly, I'm going to touch on the feature store. There's a lot of impact that this redesign has had at Grammarly, but I want to highlight one of the use cases that we enabled with the Feature Store project and talk about the impact that it's had at Grammarly. So jumping right in, there's always a debate on a data platform team of should I build or should I buy a data platform? And at Grammarly, we spent 7 years building our own data platform. We built our own Lakehouse even before it was a concept in industry. And what we found was towards the end of the 7 years, we were spending a lot of resources and energy into building our own custom lakehouse. And we looked around and saw that there were other open source or other platforms available that we could leverage and really not spend time reinventing the wheel. And so what goes into a custom lakehouse? You have an ingestion API, a storage layer, pipelining for enrichment, a query engine, and a BI visualization layer. And our team of 5 engineers built this at Grammarly in-house. And this works really well when you're a small team and you're moving fast. But over time, we found that there were a lot of scalability and challenges that we had to face. We had to really invest a lot of resources and energy into building each of these custom components. And they were scaled and built really for Grammarly's use case when it was a small startup. But as we started to grow to that next level of growth, we found that we were running into many challenges as we started to scale the system. And really the 3 main challenges that we were facing were around scalability, maintainability, and extensibility. So with scalability, this system was designed to ingest JSON strings. So any client across the company could send us any event in a JSON string, and we would ingest that data, enrich it, and store it multiple times in string format. And by the end, we would turn it into Parquet and make it queryable with our custom DSL language called GQL. And everyone in the company, product managers, analysts, data scientists would use this custom BI visualization layer with a notebook environment to query our data and perform common analytical queries like retention or funnel analysis. And this works great when you're really small and you have a few clients and a few events. Teams could move fast and iterate and send events to us, no problem. But as we started to scale, onboard more clients, more events, this becomes very expensive, both computationally and storage-wise. And so we started to run into issues by the end of 2022 with our pipelines of not being able to scale or handle JSON strings end to end. And another issue that came up was that there was no schema validation end to end. And so clients could change the schema at any point in the life cycle of an event. And this is great for clients because they just change a data type from a string to a struct, and we just ingest it and they can query the new event. But it becomes very challenging over time for data quality, reliability, and then you have this proliferation of schema. And the next challenge that we faced was really around maintainability. So with 5 engineers, we had to maintain an entire Lakehouse custom built. And we really went deep into the internals of Spark and Parquet to really tweak out and optimize all the performance that we could get with this legacy system. And we found that we were spending more and more of our time maintaining the system and really not being able to ship new features or products to our internal customers, but also our end users, Grammarly users. And so with 5 engineers, we were spending more and more time handling outages, refactoring certain components of our query engine or storage layer to make it more performant, but we really couldn't invest the time into enable new use cases. And then lastly, around extensibility, we had all these projects and use cases that we really wanted to enable with this data platform. One of them being the feature store. It was a project that I joined Grammarly for, and many engineers really were excited about enabling the feature store because we knew the impact that it could have at Grammarly. But we kept on having to push it back quarter after quarter. And I was on calls with the head of ML and intelligence, and it was devastating to say, hey, we can't really focus on this project because we're trying to keep our current system alive and scale it. And so we took a step back and started to think about, hey, how could we redesign this data platform and address some of the legacy challenges that we had with this system called NAR, and really redesign a new platform that can enable Grammarly's next level of growth. And so now I want to touch upon the event store, which is our data platform redesign. And so just before we jump into the redesign, I just want to give you a sense of the scale that we're operating at in 2021. So we had about 5 billion events. Our SLA for delivering data with internal customers was 4 hours. Again, we had 5 engineers, and we were at about 20 clients and 3,000 events. And by 2022, we had about 36 billion events, a huge jump in the volume of data. Our SLA was still the same. We hired 1 engineer, so more effective, but we had 30 clients and 4,000 events. And, with this platform redesign, we were able to drop our SLA from 4 hours to 1 hour, and we're actually landing data in 15 minutes end to end. And so this was a 94% decrease in time to delivering fresh data. And our volume of events jumped to 60 billion events. We actually doubled the team and built out the new data engineering function and separated that from DI, which is data infrastructure. And we have 40 clients and 6,000 events. So at a rapidly growing startup, our volume of data is just increasing at a staggering rate, and the variety and the amount of schemas that we're getting, and then the velocity is just increasing even more and more. And so this is really what the new data platform set out to do, and tackle these challenges while also delivering data, more reliably, quicker, so we can, take more insight, take action with the insights that we're getting from our data and build new products to our users. And so what we found at Grammarly was that the Medallion architecture on top of Databricks really simplified our architecture, and it allowed us to increase our scalability and have more extensibility for different projects and use cases. So with the Medallion architecture, we have 3 different layers where you segregate your data: the bronze layer for raw ingestion, the silver layer for filtered, clean, augmented data, and then a gold layer, or we call it a platinum layer internally, is for more aggregated or rolled up metrics. And different customers across the company can come in depending on their use case and inspect or use the data at the level of granularity that they need. And so for those of you who are not familiar with Grammarly's product, I want to just showcase that Grammarly is ubiquitous across many platforms right now, but traditionally we've been mostly a desktop focused company. And so our Chrome extension client is really one of the longest clients, has the most number of events and users. And a newer client that's been onboarded in the last few years, the mobile keyboard doesn't have quite the same volume as our Chrome extension. But as a data platform team, we have to, ingest and store all clients. And our legacy system really just treated all clients, all events the same. And this became very problematic because we have, internal clients that only send us a few hundred events or a few thousand events a day, but then we have, Chrome extension sending us hundreds of millions of events potentially, or other types of systems that we need to ingest and store. And so just really the volume and variety of data is something that we had to really rethink in this new system. And how could we really ingest the data and make sure that we could land it reliably and scalably with this new redesign. And so I just want to take you through a typical event at Grammarly and what it looks like. So with Chrome extension, we have a ping event. And so a ping is when a client opens up the browser or a user opens up the browser and they send us a ping, hey, I'm using the client or using the app. And these events are simple in definition. You have the event name, the client name, a timestamp, user ID, and then you have a bunch of metadata information that a client can add freely and then change the data type at any point in the event lifecycle. And so, this ping event is defined on the Chrome extension, but when you, scale this out to dozens of different clients, ping can be redefined over 20 different times, and it was at our company. And, other actions such as button click was defined 1,100 times. And, this is great for clients. They can move fast, redefine a definition. But when you're trying to, aggregate or consolidate all that into one table or view for analytics on the back end, it becomes very challenging to try to conform all those schemas and definitions. And this is really what happens when you don't have strict schema management and you scale it out 7 years. And you kind of have this wild west of schemas in a certain way. And so one of the big redesign decisions that we made with this new architecture was to take one event name and map it to one Delta table. So one event would be landed to one Delta table with a strict schema that we had to bootstrap initially, and then allow schema evolution for that event over time with no manual intervention. And this was a change from our previous architecture where we didn't really have a concept of tables or schemas. Everything was just stored in one giant index that users could query to get the latest event. And so we really had to, start to wrangle and get a hold over our schemas so we could bootstrap this data lake with strict schemas. And really, this would build upon our long-term vision, which is to add end-to-end schema validation for our entire pipeline. But we needed to start somewhere, and this was the most logical place to land the data into our silver layer with strict schemas and allow them to evolve over time. So I want to take you through the lifecycle of an event in this new architecture so you can see all the different components and how we leverage the Medallion architecture and see kind of the benefits that we got from this new redesign. So all clients can send us JSON events, and they get sent to a backend system called our Writer API, which is a public endpoint. And then that backend system sends events directly to Kinesis. So for a main pipeline, we typically have about 3,000 active streaming events that are sent to a giant Kinesis stream. Again, all JSON strings, no schema validation. And so this was really the logical point where we could hook in our new data platform without having to have any clients migrate or change any behavior, so we can build out this new data platform. So from here, we spun up a streaming ingester, a Spark structured streaming ingestion job using the Databricks Kinesis connector. So it made it really easy to build a config-based driven job that could read from a Kinesis stream and land to a bronze landing table. And this job, the goal of it is just to land data as quickly as possible. Doesn't really do any schema parsing. We have some metadata columns for debugging the Kinesis arrival time. But on row 6, you can see that we just have the data in binary format. So we would use the bronze raw landing table as the streaming source for our downstream pipelines. And we just wanted to ensure that we land data as quickly as possible from our Kinesis stream. So from here, we have a streaming bronze validation job. And so we migrated our legacy validation job into a structured Spark streaming app. And this job takes care of a lot of validation, making sure that all the events are coming in meet our strict security, privacy requirements, GDPR requirements. And we really wanted to make sure that we're segregating events from validated events and rejected events. So since we have a public endpoint, we receive a lot of malicious events, or clients can send us bad events. And so we want to ensure that the events that are getting populated into our analytics are actually validated. And so this is where we have these two bronze tables where we have validated events and rejected events. And rejected events can be used for debugging, or we can backfill from this rejected table, but all validated events have met all our requirements for making sure they meet our security and privacy requirements. And so the schema of this table is very simple. We pull out some columns from the event, but actually we don't do much parsing and just land the data as an event string on row 6. And from here, the next phase is where we land the data into a silver event store. And at this point, we have about 3,000 different active streaming events. And initially we tried to spin up one giant cluster where we could stream 3,000 events and write them to 3,000 Delta tables. But that was just not a feasible solution. It wasn't scalable, it wasn't performant. And so we had to take a step back and really think about, how could we repartition this data or organize it in a way where we could efficiently stream to 3,000 active streaming events, 3,000 active tables in a scalable, efficient way. And what we found was that we could actually partition our data by the client that sends us the event. So as I said, we have the Chrome extension, mobile, iOS, and Android keyboards, and other clients. And we found that we could group low volume clients, like clients that send us a few hundred or 1,000 events, into one cluster and spin up that cluster, and then use predicate pushdown to only read those partitions from the bronze validated table. And we could better utilize resources and scale up the cluster appropriately so that all low volume events would be landing at the same time, and we could utilize all our computational resources for that specific cluster. And then we would do the same for medium clients, about 7 or 8 medium volume clients. And then for high volume, heavy hitter clients, we would spin up our own individual clusters. So Chrome extension gets its own cluster that's scaled up appropriately. And what this design allows us to do is really just gives us more scalability, and really just makes it more maintainable, because one bad event from one client is not going to bring down our entire system. It would bring down one cluster, and we can still stream and ingest events into silver Delta table. And so by the end, we have an event name that comes in, Chrome extension /ping. We map that to a table name with all underscores. And all these 6,000 Delta tables live in a Unity catalog called events. And so zooming out, this is the high level architecture of our event store. And what really this allows us to do is, duplicate this pipeline, and we can spin up different Kinesis streams and land them to different Unity catalogs in a very easy and simple way. And we're not reinventing the wheel and building each component. We're really taking advantage of the Databricks platform and open source technology in the big data space. And one area I want to touch upon that was really critical in this migration was the backfill. We underestimated the complexity of the backfill, but we didn't underestimate the importance. We knew from the get-go that the backfill was going to be very important, but when you're trying to backfill 7 years of data, 6,000 different events, and all these events can change over time, their schemas, and you're trying to map it to the current snapshot of these events in terms of the schema, it becomes a very challenging problem. And we did one attempt at the backfill. We started to expose it to our users. And over time, we found that there was a lot of problems with our data. There was missing date ranges, null columns, missing events. The complex types would change, made it very difficult to map them to the current schema of the table. And we really learned a lot from this backfill. And I want to share some lessons, hopefully that would help you if you're doing a data migration. What we learned was that we really needed to invest way more time upfront building more comprehensive and automated validation jobs. We did automation for our streaming ingestion, but we needed to focus that effort on also the backfill and really build out more comprehensive reporting and tooling in an automated way so we could assess the state of the backfill and then really focus on specific gaps and areas that we needed to target in the re-backfill instead of trying to re-backfill the entire thing again and come up with the same problem. So really investing more time and resources and starting the backfill when you're starting a data migration from the beginning, really, really important and something that I'm taking away from our backfill. And then also you really should define success criteria. What does a successful backfill look like for your company? Because at the end of a backfill, it's going to be very difficult to decide, is it done or is it not? And you need to decide what events are you willing to lose that are not important. If it's bad data, you can let it go. But what events are critical for the company in terms of metrics or analysis? And you really focus your efforts on making sure that you get that backfill right. And the core of why you want to get the backfill right is you want to build user trust early on with this new data set. And maintaining 2 data platforms is very expensive, but when you're going to delete the data in one data platform, you want to really ensure that all the data you've backfilled and migrated is trustworthy and you can make that confidence in that switch. So now, lastly, I want to touch upon the event store. There's many different use cases that were enabled with this migration, but really the feature store was a use case that was previously unimaginable with our legacy infrastructure. And I want to touch upon the impact that it's had at Grammarly. So, why would you build a feature store? What are some of the use cases? We wanted to provide personalization. As Grammarly grows as a product, we want to provide more personalized experiences to our users. So we're actually learning from user behavior, their writing context. And in order to do this, you need to have a scalable way of doing feature computation. We also wanted to do rapid experimentation, build some features, test models, launch them on our experiment platform, and see, are they actually driving critical company metrics? And a feature store really allows you to do this in a very scalable way instead of one-off kind of projects or models. And so, very quickly, a feature store is just a data management system where you can easily create and store features in an offline data store and then sync them to an online data store. So, backend systems or front-end clients can get those features in real time and, adjust the product experience based on these features. And, we were able to really accelerate the feature store project on top of Databricks because we could take advantage of all the components and offerings that are built and provided on the Databricks platform. So we were able to take advantage of the ML runtime and easy cluster management. So our ML teams can come in and really start developing and training models. Feature store tables were really critical in our feature store project because we needed point-in-time querying as a critical requirement for one of the use cases. And then we took advantage of jobs and scheduling with backfill and then syncing from offline to online data source. Databricks jobs make that really easy. And we leverage DBX, which is a CI/CD workflow tool that allows us to do this all from GitLab. And then the collaborative notebook environment really made it really easy to collaborate with ML engineers, data scientists, BI, data engineers, and we have to build our own visualization or tooling. So really the feature store project was really accelerated by leveraging all the components and features that Databricks as a platform provides. And so the personalization team at Grammarly wanted to provide more personalized suggestions to our users. So at Grammarly, suggestions are really the lifeblood of our product, right? We want users to get more suggestions and actually use them and find more value out of them. And so what the personalization team found was by using the feature store and developing different models, they were able to increase the number of suggestions that we provided our users by 21%. At Grammarly scale, this is a very hard number to bump. And, this was a considerable achievement for the team, but really, more suggestions doesn't necessarily mean better product experience. And what they really pushed the needle on was the accept to look ratio. So users were actually accepting more suggestions and finding more value out of the product. And this was really the result of having feature engineering and allowing us to do online inference and get those features at real time. And so in summary, I hope you learned some tidbits and information about our journey adopting the Lakehouse architecture. My recommendation on the data platform team is to always buy and to invest into an existing data platform. At Grammarly, we spent 7 years building our own data platform, our own Lakehouse. We had 5 engineers and we got really good at it, right? We would tweak and tune and configure everything for the scale that we needed. But we found we weren't investing the right resources to enable new products, new use cases, accelerate, learning from our data and fostering that data-driven culture at Grammarly. And so we made the decision to, invest into a data platform. And this has allowed us to do more with our data and really impact customers on such a big scale in a short period of time. So thank you very much. Really looking forward to your question.
Yeah, thanks, Christian. I answered some of the questions in the chat, but we'll take all questions live now. We'll do questions maybe for like 5-10 minutes, and then we'll jump into the next part where we talk about what exactly are we buying, what are we building, how are we scaling all of this stuff with Faraz. So any questions for Christian, you can go ahead and type them in the chat or the Q&A. Who's testing all this stuff? Christian, you want to take that one?
It's testing all this stuff. Yeah, data quality is an important area that we're investing in. When you have a large number of events, you can't really take advantage of all that data. And so you really need automated tooling to test the data quality and test that, the data is landing in the way that you expect from each layer, the bronze, silver, and then gold layer. And so we have a dedicated data engineering team that really partners with other stakeholders to inspect the data, have reporting, and ensure that the data that is actually landed is useful. And then they help report to us like, hey, maybe there's a problem with our upstream system. But we work very closely with our stakeholders and inspecting the different events and making sure that they look and behave in the way that we expect, given the volume and history of the data.
We have a couple questions that I see that are going to get answered in the next conversation, so we won't do those ones just yet. You can answer this one, Christian.
And I think one thing to add with the testing, like we also have integration testing, unit testing, like in the event store system. So like we've spent a lot of time making sure that the components themselves are well tested, and then data testing is another separate component.
So you want to talk about the difference in the tech stack, basically with NAR and Databricks now? Someone asked about our cloud usage and stuff.
Yeah, NAR was built on top of AWS using Parquet as the underlying data format on top of S3, and then we have a MySQL database that manages the metadata information, and then everything is run on EMR. So we have a whole pipeline of EMR clusters that ingest data, landed into S3, and then other downstream pipelines reads that and does the transformations and lands them in S3 again. Yeah, all on Spark, mostly in a batch-oriented way. We actually have long-lived clusters, but we do batch processing on them. So we actually weren't really taking advantage fully of our clusters because we have this batch-oriented model, but for long-lived clusters, so it becomes very expensive. And with Databricks, we're actually doing Spark structured streaming, and really utilizing all our clusters in a better way.
So for the people asking questions about security and deletion and stuff like that, we'll do longer talks. I don't want to try to answer those types of questions in 1 to 2 minutes. So we'll do future talks about data security, data compliance, all that stuff. What do you use to store and serve gold data? We'll talk about this a little bit in the next talk, so let's hold that one for Faraz. Any other questions before we move on to the next piece? Okay, let's go ahead and move on. If you have questions for Christian, he'll hang around. You can still add them in the Q&A, and then we'll come back and answer them in a little bit. Okay, so let's go ahead and get going on the next part. Okay, so this is actually going to be something that we share at the Data and AI Summit as well. We're going to do a smaller scaled down version of it here for you today, just in case you can't make the conference. But if you're going to the conference, I recommend you come check us out. You can ask questions in person. We'll go in a little bit more detail during those sessions as well. Okay, so like I said, my name is Chris. I've been working on Grammarly's data platform for a little under 3 years now. I'm going to give you a quick intro into Grammarly, as well as help you to understand our scale a little bit better. I know Christian touched on that, but I'll also give you a high-level walkthrough through our architecture, and then I'll hand it over to Faraz, and Faraz will do a deeper dive into a component that he worked on recently, which really helps us to scale these systems faster with limited resources. So I know a lot of people in here are excited about LLMs and NLP and AI, and we are too. Grammarly's been in this space for 14 years, writing with our users, but a special focus on protecting data, protecting your users' privacy and all those things. But we're still really excited to show you what work will look like for teams using Grammarly Business. So I wanted to quickly show you a 1-minute video that we released recently that highlights that. So as you can imagine, it's a really exciting time at Grammarly. We're rolling out a ton of new things, really, really exciting. But let's just go ahead and jump in by actually going back in time. These are numbers that Christian talked about a little bit earlier, but let's dive into them a little bit deeper. So November of 2020, this is actually when I started at Grammarly. The data platform team was handling around 5 billion events per day. And how do we get to that number? Well, let's say that you're writing an email. If we find a suggestion, that would be 1. We send it to you, that would be 2. You view it, that's 3. You close it or change it inline, that's 4. We show you another one, 5. And that's just one sentence. So with 30 million daily active users, you can see how we could get to 5 billion a day pretty easily. We also had about 350 employees. This is a AI NLP company, so they're all very, very data driven. So you can imagine that all 350 of those people were data platform stakeholders. And we had 5 engineers working on all aspects of the data platform, like Christian mentioned before. And when I say all aspects, like Christian mentioned, that's a lot of different components. So we did handle ingestion. We even handled API integrations. So things like integrating with Salesforce and ads APIs to bring in that data. We owned business logic and pipelining all of that logic into our data. So you can imagine scenarios like a user is doing things while they're signed out and then they sign in. We want to push that user ID back in time. Those are things that we also owned. On the storage layer, we owned access control. You can imagine in a distributed file system, this is very, very complicated stuff. So we spent a lot of time there. We also had to handle cost management and even things like custom query languages and visualization in the analytics layer. Anybody in here that's a backend engineer, you're probably not pumped when you hear UI work, but this data platform team was actually managing a full UI as well. So 5 engineers scrambling between all of these different components was very difficult. Another thing that I want to call out in this world was that this is a very sequential pipeline. So each of these boxes happen one after the other, and they can't skip over each other. So on a good day, 4 hours was our SLA for data latency to get from one end all the way to the other. But on a bad day, one of these stages might go down. So let's, for an example, just pretend that data attribution right here goes down. So at 5 billion events a day, that's actually 60,000 events per second. So every second, 60,000 events waiting, and just building up behind that broken process. And so the team was under a lot of pressure to stand things back up really quickly when they went down. And as you can imagine, with 60,000 events per second building up, that creates a tremendous backlog, but also next processes, downstream processes, now have a tremendous volume that they have to deal with. So typically when we had one issue or one outage, it would create many, many outages across this entire pipeline. Beyond that, because we have 5 engineers and we're managing so many different components, it was very, very difficult to add features, which, as you can imagine, with a growing company, a growing data-driven company, could get very frustrating for our users. So new business logic requests, new UI or visualization features, even new pipelines was stuff that we really had to push back on. And we started to realize that this just wasn't going to work. So that's when we started to reimagine that data pipeline, that data platform in general, and Christian covered a lot of that earlier. So let's fast forward to today. We more than doubled the team. So we're now at 13 engineers on the data platform team, which is, that's great. It's exciting. But at the same time, the company has grown at a similar rate. So what that means is that all of those backlogged requests, all of those people asking questions and requesting things of the data platform team has actually continued to grow throughout this time. So we haven't really dug out of that hole yet. Beyond that, our event rate has gone through the roof. So we went from 5 billion events today all the way up to 60 billion events per day. This is typically a hard number for people to actually understand. So I like to extend that to a full year. That would be 20 trillion data points a year. And even still, that is hard to wrap your head around. So let's do another example that I like. Let's imagine every one of Grammarly's data points across a year is a penny. And today, next to you, next to your computer, you're going to start stacking pennies to create a tower. And you're going to stack 20 trillion of them. That tower that you've just created is going to be tall enough to reach the moon and back 45 times. It's a ton of data in just 1 year. So even if we put all of our data in one place, that amount of data will create data chaos. And what I mean by that is, even as a data professional, you come in to see 20 trillion data points, you're going to have a little bit of option paralysis. Where do you get started? How do you actually know that you're creating queries that are efficient, queries that are efficient, which means producing the results that you think they're producing? This becomes a big, big problem, even for most advanced data people like data science and even data engineers. So this is where data democracy comes in. This is a term that maybe you've heard before, but what this basically means is that we want to provide every function with the access that they need, no more, no less. So we really want to help with that option paralysis by limiting the amount of data points that people can see. With a company like Grammarly, our primary focus, especially in the data platform team, is user trust and safety. So any opportunity that you give us to be better with compliance and better with security, we're going to gobble that up. And so this was a great opportunity for us to even improve our processes. So for us, Lakehouse was the way to actually accomplish this. Databricks is our unified data platform. Okta syncs with Unity Catalog to roll every user into a role or a team. And then Unity Catalog handles all of our access controls, whether that's tables, files, columns, notebooks, everything. We already spoke about this briefly last year, so I'll make sure to provide the link to that, but it's also on my LinkedIn if you want to go check that out. But let me give you an example of this pyramid specifically, and let's use an example that probably all of you know, daily active users, DAUs. This is a relatively simple metric that most companies have. But at a company that's growing and evolving as fast as Grammarly, it's constantly changing. So at the top of the pyramid, what will happen is that BI will create a dashboard that has DAUs over many different cuts so that leadership and managers can go in and see how is Grammarly doing with DAUs at a high level without writing any code, very clean, very consistent. BI will work with product managers, with leadership, with engineering to make sure that as Grammarly evolves, our definition of DAUs also evolves. And then they'll go work with DE, data engineering, to make sure that DE is able to create curated data sets that are highly optimized for querying such things. So what DE will do is build a lot of great tables that have a wide range of dimensions for cutting DAUs. Again, a lot of times that will feed into the BI dashboards, but it basically gives you another step of granularity to answer the questions. And then finally, at the very bottom, you have data infrastructure, or DI. DI really wants to make sure that you have all of that raw data. But again, Grammarly is at such a huge scale that we do have to put some priority on these things. So DE will work with DI to help us to understand which of these events are most important. Maybe we can make them more reliable. Maybe we can make them available faster, like real time. And these are things that this pyramid really helps us to achieve. Basically, the main takeaway I want you to have here is that every step of this pyramid, we want to know the answer to the question why. So if someone goes into a BI dashboard and sees a drop or a spike in DAUs, data engineering tables will typically help you to answer that why. And if data engineering tables aren't able to answer that why, going into the raw data and all of those different events that make up DAUs will definitely get you to the answer. Beyond that, this pyramid kind of represents data volume. So if you start at the top, you really make it easier for yourself. Data science even will typically start at the top and work their way down, even though they're very, very capable of working on any level in this pyramid. Okay, so before I show you our new architecture, I wanted to throw this back up here, but the main things I want you to just see here again are we had one way in, streaming. We had one way out, which was nar GQL. Nar is the name of the UI. GQL was the name of the language to access these things. It's just a SQL-like language that interprets into Spark. And finally, that our SLA was 4 hours. So this is our architecture now. It's still at a very high level, but what you can see here is that we actually have 4 ways in now: streaming, batch or micro batch, CDC, which stands for change data capture, and then one other, which is an API integrator that's not shown here, but I'll show it in the next slide. We actually have 8 ways out on the other side in the analytics layer. So as far as languages, you can use SQL, you can use Python, you can use Scala, you can use GQL, basically whatever you're most comfortable with, whatever your job requires. We want you to be able to use that. And this new model has helped us facilitate that. Beyond that, we have Tableau dashboards and Databricks dashboards, like I mentioned at the top of that pyramid. We still kept the NAR UI, so people could still do very, very custom analytics, but we linked the NAR UI back to Databricks data. So we still have that data parity and consistency. And finally, the feature store, which Christian talked about in the last talk, helps us to do experimentation and personalization so that all of these insights and models are actually helping us to make your user experience better. Another thing I want to call out here is that our latency dropped down to 15 minutes. This is not our SLA. Our SLA is actually 1 hour, but we're consistently hitting this 15 minutes. And a lot of these data points we can now make available in real time. The main takeaway here is, like Christian said, you don't have to buy everything, but offloading a lot of these things to Databricks really, really helped the team. So we're no longer thinking about access control, which is a huge, huge piece of work. We're no longer thinking about query. We're no longer thinking about visualization. And again, even with 5 engineers or 13 engineers, we can now refocus them to actually solving Grammarly specific problems. So I know this looks pretty and it's nice to show on a slide deck, but let's zoom in a bit and make this a little bit more detailed. Okay, so don't let your eyes glaze over here. I know that there's a lot on the slide right now, but we'll step through each of these and it'll all make sense. So let's start with the easy part. Down at the bottom, you have Fivetran. Fivetran is just an API integrator. There's a lot of them out there in the market, but we use Fivetran to manage about 16 external connectors right now. Across different ad platforms, survey data, things like that. Just making sure that we bring all of the information into Grammarly so that we can use it. Again, we are a lean team, so we want to offload low risk items. Yeah, I mean, it's really easy to build an API integration like that, but 16 of them and then managing them, there's updates, deprecations, all kinds of things. It's very, very tedious and time consuming. So this is a great target for buy. And that's something that we did really early. So basically, Fivetran syncs all of our external data to Unity Catalog, which obviously we then automatically limit access to, and we actually limit access by connector. Okay, so keeping going, change data capture. This is a very similar concept, actually. So across Grammarly, engineering teams can stand up their own databases. We want to give them a framework that allows them to basically copy that data into Databricks so that other teams can use it for analytics. So what we do is we set up a framework that allows them to sync all of their changes, whether that's an insert, update, a delete. And rather than doing full copies, we stream all of those changes into Databricks and then basically rebuild that entire database for them using their transaction stream. This is something that we'll talk about here in a little bit as well. But again, it writes to Unity catalog, and then we automatically limit access based on the database owner. So that, again, we're not worried, and engineering teams are not worried about access controls. What you see here is actually way more than we have time to talk about today. This is where all of those 60 billion events a day are processed. It's a really, really interesting migration that we're going through right now, going from schemaless ingestion to schema-enforced ingestion. I promise we'll talk about this in the future. But basically what I want you to know here is that our motivation is to increase data quality. This leads to more reliable real-time data, which is obviously very important to Grammarly, but it also increases data uniformity. And data uniformity allows us to use framework-driven pipelining. So what is framework-driven pipelining? It's actually a great question. Again, we're a lean team. We don't want to build custom pipelines for every piece of business logic or for every request from all of those 900 people that are requesting things from us. We want to rely on frameworks. And lucky for you, that is exactly what Faraz is going to talk about. So I'm going to actually stop presenting and pass it over to him.
All right. So do you see my screen?
Yep.
Okay, cool. Hello, everyone. My name is Faraz Yasrobi, and I'm a software engineer in the data platform team. I've worked on our data democratization project for the past couple of years. And today I want to share my experience in this project and also the framework that we built to solve our data engineering problem. Okay, so where Chris left things was, okay, we landed the raw data. This data comes to us like through 6,000 fact tables. We also have this CDC service where we replicate the data and we land it, and we have those dimension tables. Now we want to give access to people to do their data analytics, build their own data processing, and so on. My first instinct as an engineer is that, okay, let's not do anything, just give people access to the data and let them do whatever they want. But this is not going to work. Actually, I think this was also one of the questions that happened in the QA. If someone tries to union like a 100 table from these tables and then do something with it, that's going to be very expensive. It's going to perform very badly, and it's simply not going to work. Another major challenge with this is that when you have a lot of tables, data discovery is going to be very challenging. But so for that reason, we need to have some middle step. That's where the data engineering comes into play to solve that problem. The whole point of data engineering is to identify querying patterns that our users have. So instead of them repeating those patterns over and over again, for example, there's this events table everyone wants to query, and there's this other dimension table that everyone wants to join with that event table. There's no need to do this over and over again in the query time. We identify these patterns, we build fundamental data sets that all those operations happen in the background, and then users can query those published data. That's going to be very faster, it's going to be cheaper, and it's going to be more accurate. Because raw data usually has some data problem. We also solve those problems. So the data that we offer to our users is high quality, it has like a good querying performance, and it's cheap. My favorite analogy is for data engineering is oil refinery and crude oils. Crude oil is very valuable. It's arguably one of the most important things on planet, but it's useless as it is. It has to go through some refining process, so we can turn it into gas or other products and use it for different purposes. The two major questions that usually you will have next is that, okay, what tables should we build? And how do we build those tables? In terms of what tables we should build, there are two aspects to it, structure and content. I'm going to talk about the structure part, but not the content part, because that's derived by business intelligence and by business logic, and that's a data science business intelligence world question. But data engineering, we can define the structure of the tables and how do we build those tables. That's why we introduced a framework called Refine. It's short for Data Refinery. This framework is built to enable larger scale data engineering. As you can see at the top right of the slide, this framework has 5 table structures and it has 4 builders. What the developer does to build a data pipeline is basically connecting these builders and tables like Lego-like building blocks. If things are supposed to fit, they will fit. If they're not supposed to fit, they're not going to fit. And you will know that very early on in the compile time, not after you deploy and wait for hours for your job to run. And this framework also does, it manages our tables. In my next slide, I'm going to talk about what manage tables means. And it also manages the processing. And in the bottom right, you can see one example of this pipeline end-to-end, where we have the raw data, their fact tables. We connected builders, in this case, fact roller and dimension builder. We produced new type of the tables. We connected that to another builder, and we produced another type of table. This is just one example. In real world, like in our world specifically, this can go very deep. Like we have 4 or 5 layers of this system, and it's really important that this whole thing works end to end. Any issue upstream will translate into a lot of issues downstream. So we solve this problem through a framework to address these kind of issues. Let's talk about the features that this framework offers. I split the features into 2 groups, builder features and storage features. I'm going to focus on builder features mostly because storage features are mostly already solved. For example, for automatic optimization and vacuum, we just use Databricks tools. Databricks gives us this optimize command where we can run on the table and it's going to auto compact the thing. Doing it is just a matter of scheduling that command. But builder features, like how we actually build those tables, that's the challenging part. And among the features that we offer, the first one is incremental processing. We use Spark structured streaming end to end, so there's no need for manual offset management. You don't need to keep track of what day's data is complete. Do I need to recalculate it? Are there any gaps in the data? We just use Spark structured streaming, which comes with offset management out of the box. Another feature of this framework is it produces consistent data. One of the most challenging things in a data engineering is that data arrives in different orders. Like as Chris mentioned, like we had a lot of pipelines, like Fivetran, our database replications, a lot of ingestion pipelines. Any of them might have a problem, so the data is going to be delayed. There's no guarantee that things will arrive in order, and this produces a lot of inconsistency. Our framework handles late arriving data by using stateful processing to address this issue. I'm going to have more context on this later. This framework is also type safe. We use Scala case classes and Spark dataset end to end. So everything is type safe, and this prevents a lot of problems like one of the common things is that when you build a data pipeline with data frame API, you are going to have a lot of column not found errors in large scale because someone else changed something in some pipeline. A lot of downstream tables are being affected. This is basically the data lineage issue. We also offer backfill tools. Backfill is arguably more important than building the table itself because data engineering is an iterative process. When your stakeholders come to you with a problem, they have a good understanding of the problem, but usually they don't know 100% of what they want. They come to you with 60-70% of the requirements. You build the first version, we do some validation, we figure out what's missing, and then we do a backfill of that process. And over time, requirements change, and we have to repeat this whole thing. So it's really important that we can quickly backfill things, and this will minimize productionizing the products from the development phase. All right. Now, as I mentioned earlier, we have 5 table structures within this framework. I'm going to quickly go through these 5 table structures to give some context on what they are. The most common table structure that we have are fact tables. Fact tables are basically just a timestamp. There's a timestamp column, and there are a bunch of information. For example, we talked about suggestion accepted, suggestion rejected earlier in the presentation. When users accept a suggestion, we receive an event, and there's a timestamp associated with that event. And we get a lot of these, 6,000 tables with a very high volume. The most important characteristic of the fact table is they have unbounded volume. There is no guarantee that within a specific time interval, like 1 hour, there's no guarantee that there is a maximum to the rate of the event. Users can produce a lot of events within a short time interval, and that can cause a lot of problems downstream. To address that issue, it's a common practice to introduce time series tables. Structure-wise, these are very similar to fact tables with one difference. They are very low grain, and they are basically low grain representation of facts. So because the data volume is high, so let's group them by hour and keep some statistics for that hour. This introduces some inaccuracy, because you basically have one data point for that 1 hour interval, versus where if they were facts, you would have a lot of those data points. Next table structure that I want to talk about is dimension, where like a timeless dimension. As you can see, forget about this created timestamp column. There are no other columns that represent time. This is basically an entity table. In this example, Grammarly has this product, Grammarly Business, where we sell to the enterprise customers. We have institution table to represent the institutions. For every single institution, there is only 1 row. Also, this type of table is commonly known as a CD type 1 in the industry. Another type of dimension table is dimension history, where we have this table structure provides information about how the entity has changed over time. Same institution that you saw in the previous slide has 3 rows in this table, saying that, okay, starting from this timestamp, ending at this timestamp, the value of the user was the other columns. Then we have another row representing another window. The core characteristic of this table structure is that it enables point-in-time querying. You can easily join this table to some fact table and then have the fact enriched correctly with like a point in time. And this table is known as SCD type 2 in the industry. Last table structure are dimension snapshots. One of the common table structures that people really like is that, okay, let's capture state of all the institutions, all the users at end of the day, and have that data and keep that data. This is really useful, especially for ML teams. Like, it gives you like a low-grain data, state of all the entities is determined, it's easy to use, and actually we widely use this type of table as well. Now, let's talk about the 4 builders that I mentioned earlier. First builder, which we needed, was, we call it fact roller. What it does is that it basically takes a fact table or time series table, does some group by time window. You can also optionally have more group keys, and then produce a time series table. For example, here we have 3 inputs in our fact table. They all happened on January 1, but at different times. Our output for that is 1 data point for January 1 with 1 value. And that value is basically sum of the input values. Probably the only purpose of having a fact roller in the system is to control the volume of the data. We have all these suggestion accepted, rejected events in our system. They are very high in volume, and there's no point in processing them one by one. Adding hourly inaccuracy or daily inaccuracy in these tables doesn't hurt the business logic at all. So we turn them into time series tables. So downstream, we have to deal with lower volume of the data. And how this whole thing works is that the developer only needs to configure this builder. We have some code in here that you have to write. It's just basically a Scala function. And you write that function. We translate that to Spark code. And what kind of a Spark code? It's a stateful Spark structured streaming. And this code will read a data set and write a data set. So another thing here is that, as you can see, sorry about that. As you can see, there's a Scala case class on the left and Scala case class in the right. In this case, both are the same. This represents the data model. We have a one-to-one relation between our data models and our tables. And this is very easy to work with because Spark is natively integrated with Scala. So you can easily read a table as a Scala case class. So what this builder is going to do is that read that table as a data set of that type, run the operation, produce another data set, in this case with the same type, and write it to the table. A user doesn't have to do anything. They only have to write the config. Another builder we have is dimension builder. This is one of the most useful things that we have. Dimension builder, the purpose of this builder is to aggregate facts incrementally over time. For example, we have this facts table on the left for each same user ID 1, 2 different timestamps. They have this test property. In one instance, it was 100, and in another instance, it was 50. We want to accumulate this value over time and know that, okay, what was the total property 1 total value for this user over time? A dimension history table will look like this. Starting from January 3 until January 10, the value was 100 because the first row is 100. The new row comes in, we sum it, and now we have 150. Again, we have same structure. There's a config. User implements this sum function, basically. They get this code, they implement it, and we turn it, and we do everything else. At the bottom, it's the same structure with one difference is that in this case, our input model is not same as our output model. And this is a case that we support, and it's totally fine. The third builder is fact hydrator, also known as enricher, where we have a fact or time series table, for example, this one, and we join that with the dimension history table and enrich facts with information about the user. For example, this user had 2 events on January 3 and January 10 with two values. So our hydrated facts will have exact same events with exact same timestamps with one additional column called user type, where it says that at the time of the event, what was the user type? We get that information from our dimension history table. Under the hood, the structure is very similar to previous ones, with the difference that this builder takes 2 event streams with 2 different data models and produces another stream with a different data model. And the last builder is dimension joiner. Why we needed that? Because we need to put together our dimensions from that we created earlier. When you have a lot of data streams, you are going to create these dimension tables from different streams. They are not happening on the same stream. So you might create this dimension from one stream, this other one from another stream. Now, but what you want is to have them in one table. Why? Because joining data to multiple tables is expensive. But if we consolidate them into a single table, it's going to be way performant to join with a single table. And under the hood, the structure looks very similar to Hydrator. We have two input data sets and one output data set. Now, I want to talk about one of the challenges that we had to solve, which was data consistency. I mentioned that data consistency happens because of the late data arrival. And here is one example. This is a case of fact hydration. We have a facts table at the top, and we have a dimension table under it. We hydrated the fact with this dimension, and that's the result. So starting January 1, the user was a free user. Event happened on January 3, so the user type is free. Now, let's say user receives an event on January 7. We still have the same dimension history. We hydrate it and create this free user. But then another row comes in, this time in the dimension history table. But this row arrived late. This happened at 8 a.m. The previous event was happening at 8:10. In an ideal world, we should have had premium here, but because this event arrived late, we populated as free user, and this is wrong. The data right now, we have wrong answer in the result. So if you don't handle late arriving data, what's going to happen is that depending on when you executed your pipeline, you're going to have different results in your output stream. And this is data inconsistency. And this is really bad, because when your company grows, metrics matter a lot. For example, the DAU metric that Chris mentioned, it's the most fundamental metric in the company. All the teams rely on that metric. If you keep changing, okay, if you publish that metric wrong, that's going to cause a lot of problems. Also, it's going to make the whole system ineffective. Okay, how do we solve this? Generally, there are two solutions that work. We looked into a bunch, but these are the two solutions that are widely used. Number one, so our SLA is 1 hour. We know that the data is going to land in 1 hour. So before doing any kind of processing, let's wait for 1 hour to make sure that, for example, yesterday's data is complete. At 1 a.m., we launched a pipeline to calculate the previous day's data. This works. This is actually, I think, the most commonly used method because of its simplicity, but it creates a lot of problem. Why? Because of the data lineage. Our pipelines are multi-layer pipeline. We have a pipeline, we turn table from one form into another, then we have another builder, then we have another builder, and it goes on. If all of them have to wait until their late arrival threshold passes, the final table is going to deliver the data 10 hours late. And that's not acceptable. And that causes a lot of problems. Like imagine a product team has a release and they are not going to be able to understand how the product is working until 10 hours passes. And that's a big problem. Another method to solve this problem is by using stateful streaming. How we do that? Okay, let's remember the recent inputs and recent outputs and output updates that were incorrect. For example, in the previous example that I mentioned, if this pipeline that was processing this, if it knew that what was the recent output that it produced, and then it received this input, it has the option to go and fix it. And that's exactly what we do here. How do we do it? We utilize stateful streaming. Flat map groups with the state is one of the functions that Spark provides, and it's my favorite function in Spark because it's very flexible and versatile, and basically you can do anything you want with it. But it's not commonly known, and people usually don't use it, mainly for two reasons. Python support was just added recently. I think it was 6 months ago or something. Spark 3.4 has this feature for Python. Before that, Python support was not there. Most Spark users are Python users. And the other one is that it's complicated to code. It's complicated to implement a pipeline in a stateful way, which works great for us because within our framework, we do the Spark coding ourselves. Our users don't do it. So we go through this trouble once for each builder, and this problem is solved forever. People don't need to deal with this. Now, a little bit about how this function actually works. You read the stream like any other stream, you convert it to a typed data set. So for example, here we convert it to a data set of type I. We do a group by key where we provide the grouping function, then flat map groups with the state where we do the aggregation. What does group function does? For example, if it's a fact stream about users and you want to group by user, each user ID's data is going to separately go into a different aggregation function. Now we have iterator of input data. We run this aggregation on top of this, your group keys, your user ID, and you have a group state. This group state is where we store recent inputs and outputs. Now, this iterator of I is the new information, the new batch of the data arriving. Within group state, we have the inputs, recent inputs and outputs. We do some complicated comparison between these two and make a decision, what should be the output. Some of these outputs are newly created rows. Some of them are deleted rows. And some of them are updated rows and some of them are newly created rows. We also support delete, but that's complicated. I don't want to get into that right now. And at the end of the operation, we go back and update the group state so the next batch of data can process correctly. One other feature that this framework has is type safety. We can detect schema issues in the compile time. This significantly reduces our maintenance time, our development time. It's awesome. And the reason for that is if you go to conventional data pipeline building, we are going to use data frame API. In the data frame API, you read the table as a data frame, you do something with it and write it somewhere. There's no type safety to it. And very possibly someone upstream can make a change that kill your pipeline downstream. For example, this change. Upstream team decided that this property one in my fact model is a string. It's not int anymore. In a data frame world, this dimension builder wouldn't know about this. It would run, the job will be deployed, the Spark function will make progress, then you are gonna hit not column found error, like an incompatible type error. And this is not good. But within our framework, because we're only using dataset and dataset API and Scala case classes, this will fail in the compile time. You won't even be able to productionize this code if it's causing some data some type issues downstream. So this saves us a lot of time. Especially initially when we were developing, we were constantly changing things. And just being able to find your errors in the compile time was very huge for us. And that's it. That's my that was my last slide.
Thanks, Faraz. I can share real quick and then we can run through some questions. There's actually a question relevant to what you just talked about. So let me throw this back up. And by the way, let me go ahead and plug, we are hiring globally. North America and Europe. So if you want to join the data platform team, if you see something in our architecture that you think is dumb, we would encourage you to come join us, help us make it better. Lots and lots of open roles at Grammarly. So if you hover over that QR, you can go to our careers page and check out all of our open positions.